So this is lab number 7. We're going to start out with step 1. So we have our folded filter paper. We're going to get the mass of it. Write that down in your table. So this is set up now in our funnel. We have a long stem funnel. And we will get this set up. And down here will be a collection flask in a moment. So step 3. Here we have the lead chloride. I want you to notice this. This might be important for some of your stuff later. Notice the percentage, how error may be coming into that formula weight. That makes it nice too whenever it's already on the bottle. That'll help you in your calculations. We've had this sitting overnight. We have excess of this white powder, lead 2 chloride, that has been dissolving overnight. And so we know this is saturated. Now the supernatant is any of the solution above where the solid, or if there were any type of disturbance. So whenever we pour this out, we're going to notice that some of this is going to get disturbed. So we don't want any of the solid to be in the liquid that we are going to be using. Okay? So we're going to take this. We're going to do this a little different than the instructions. So just bear with me. So we're going to remove the stir bar and then we'll look at it. So we're going to pour this as much as we can without disturbing any of the material in the bottom. So this is saturated lead 2 chloride, no solids. We've got way more than enough, so I can stop. So notice not much of it was disturbed, but if you were to have allowed that to shake up, you could have gotten some of that stuff to get suspended for a second, and that would have caused some problems. Said that we needed to use a graduated cylinder, and we were going to pour that material straight out of the container into the 100 milliliter graduated cylinder. Something a little more precise is the 100 milliliter volumetric flask. So we're going to pour this in to this because we are using exactly 100 milliliters. This will measure that. Notice I said we got more than enough put into this beaker. It was a clean beaker. It was washed and rinsed with distilled water last night and dried. Same with this pipette. So this, I'm going to use my pipette here to add enough that the meniscus is lined up with that line, and that will give us as close to 100 milliliters as possible. And now we will transfer that to the reaction glassware. So in step 3, all we're going to do is add our material here to our 250 milliliter graduated cylinder. So what about those little drops in this? Here's what we're going to do. We have measured in this originally and poured into this. We've already got the moles of this, but what if any of these moles of this material, because there's just a little bit of liquid still there, maybe only a few drops, maybe only a half a milliliter. If I add distilled water to this, yes, that's going to dilute it, but the actual moles that we are looking at in our stoichiometry is still present. So at this point, the concentration doesn't count because we've already done the measuring, got the moles of the lead chloride that could be in here, and so that is not going to affect any type of calculations. So step 4 says add 20 milliliters of 0.5 molarity, that's moles per liter, of potassium iodide solution to the beaker containing the lead chloride solution. Well, here's the problem. I have used all of my solid lead iodide to precipitate out leads for some of the other labs that we've done to dispose of it properly. And so all I've got left is some 0.1 molar potassium iodide. Well, 0.1, it takes 5 of those to make 0.5 molar. Well, 5 times 20 milliliters is 100 milliliters. So what we've got, instead of measuring out 20 milliliters, we're going to measure out 100. So this is the one that is just been used for the measuring of the 100 milliliters of lead chloride. We're going to use another clean one, another dry one, and we're going to measure out 100 milliliters of the potassium iodide, the 0.1, because we don't have the 0.5. And then we're going to add that to our lead chloride. So not part of the lab, but because I don't have the potassium iodide, would it have mattered? This is a question for you, just to think about this. Would it have mattered if I used sodium iodide in this case? I have plenty of sodium iodide. Could I have made up some 0.5 molar sodium iodide and replaced that? So as we go on, now the next step is to add our 100 milliliters. And hopefully you're understanding that stoichiometrically, if I know what the solubility of this is, I'm going to add excess of this. I'm going to add more potassium iodides than necessary. So in this, which was originally supposed to have been 20 milliliters of 0.5 molar potassium iodide, now because I only have 0.1 molar, I am going to add 100 milliliters, 5 times the amount of 1/5 of the concentration, same moles. And I'm going to add this slowly and see what happens. Try not to let that spatter out. So we got this nice yellow powder precipitate that has been formed. Now, I said that we've used more than enough of this. This is in excess, so I'm not going to clean this out and make sure it all gets in there because we got to bring this to boiling anyway. So I'm just going to clean this out. This we've got to boil to make sure that every bit of these potassium iodides, specifically the iodides, will mix with the lead 2+, so that they will actually become good. They're going to come into contact with one another and they are going to react and form the precipitate. So after step 3, we were supposed to draw this diagram of the beaker. Notice it's only about half full. And we were supposed to indicate what is dissolved in the water. Well, we know it's lead 2 chloride. And so it's aqueous, it's all dissolved, there's no solids. So in the aqueous state, they are floating around separately. We've indicated the charge. More importantly, what is the ratio? We'll come back to this later. So we've got this on the hot plate. We are heating it up. It is going to get to the boiling. We are going to stir occasionally here at the bottom. Notice how some of this gets right there on that stirring rod. We don't want to take that out and wipe that off. So what we will do is leave that stirring rod in there. Hopefully it doesn't get too hot. If it does, we're going to wear some gloves and make sure it doesn't burn our hands. But we're going to rinse this off. We're going to rinse that yellow material down in there because that is part of the stuff we've got to measure. And if we lose that mass, that could affect our results. So now that we've added the potassium iodide to our solution, it looks a little more like this. So we added the potassium iodide, but is that potassium iodide together? No, we know it was dissolved. So as an ionic compound, we have pluses and minuses, don't we? Do those two come together? No. Do these two come together? Well, we know that potassium is always soluble, so that's not going to happen. So potassium is never going to precipitate with anything before it's solid. So the iodine and the chloride is not going to come together, but could an iodine and a lead come together? Yes. So these two might come together. So we're going to circle these, all right? And so another potassium might be down here because it's going to mix, and another iodine is going to come in here. But wait a minute, is this going to cancel out evenly? No. If we added another potassium and another iodine, yes. Now we're going to have two of these for every one of these. That's going to then, whenever they form together, what are they going to do? That's solid because it's denser than water. Makes sense because lead and iodine are probably pretty heavy, right? So that's going to happen. We're going to add another potassium and another iodine here. And what's going to happen here? Because we're going to give this plenty of time, we're going to add some more potassium. Of course, it's all going to mix. An iodine, another iodine, another potassium. My K's. So this is going to precipitate out. Hopefully, every one of the leads is going to mix with two iodines so that every one of the leads fall and become this yellow solid material. So that's kind of what we're looking for, and this is going to help you to solve and write out a lot of your answers to the lab. So at this point, we've noticed that this yellowish stuff is starting to just now boil. It really is getting almost all of the material out of solution because there's not these little fine pieces suspended. We can see now that we can see through it. So that means there's not a lot of this little fine stuff floating around. All of the lead that is going to react, it probably has. And so it's also making our crystals larger. So these crystals, remember, any ionic compounds, they like to form repeating units. And so whenever we increase the heat, that's going to allow all of those things to come into contact with one another. But as this cools, the crystals should or may get a lot larger as they, some of these are dissolved in the water at a higher temperature. But as they cool, then what's going to happen is they are going to become less soluble in colder water. So we are about ready to let this start to cool off, and then we will decant. To be able to get this filter paper into the funnel, we want to try to touch it as least amount as possible. But to get this seated, we're going to add a little bit of distilled water. Try to get this seated all the way around. There we go. Now we can use our glass stirring rod. Now we're going to hold it like this, and we're going to use this to pour the material. Notice what it does. The adhesion of the water molecules to the glass. We can direct this down. We do have a little bit of the material that decided to float and stay at the top. We're trying to disturb this the least amount possible. I've allowed this to cool down enough where I can touch it. But if it has not reached 25 degrees Celsius yet, or room temperature, if it's still warm, how is that going to affect our results? What would happen to the solubility of this lead iodide? So we're trying to decant this, just the liquid, not the solid, here at the bottom. Notice we got some solid here at the bottom. We're trying to decant this through the filter paper. before we do our wash. We definitely cannot allow the liquid. Oop, we're starting to get into some of the solid now, so we're going to stop. All right. Let me take this out of the tripod so we can see this is going to filter. As it comes down the long stem funnel, the cohesion of the water molecules to itself actually creates a tug of war, and it pulls the water down faster. And as we get this long stem funnel, it is touching the side of this flask, and so that the mass of this water down here literally pulls the water through this filter paper faster than if we did not allow it to touch, or if we used a short stem funnel. One thing that we do demonstrate if we were in the lab is we would do one with a short stem funnel and a long stem funnel, and this would go quite a bit faster. And so if we are looking at our filtrate, notice we're not getting any little yellow specks, so that's good. That means we're getting all of our material caught in our filter paper. So now we will wash this 3 times and filter it, and then on the 3rd time we will actually try to get as much of this solid into it as possible. So when I rinse this, I'm trying to rinse as much of this as possible. And we will decant. And yes, some of this solid is going to get in there. We're going to again rinse this a 2nd time, getting all of it down on the side. The purpose of this is to try to get all of the potassium chloride through. We want to get it rinsed out as well as possible. Because remember, this potassium chloride that is still in there, if you get rid of all of the water, its mass will still show up in the filter paper. So we want to rinse this as well as possible. So this last time, rinse this as best we can. Then we're going to do this, and then we're going to dump it. Before we do that though, we want to let this get through. All right? Okay, so the other material has filtered. We're going to rinse this one more time. We're going to create this slurry and try to get as much of the solid in there at once as possible. We need to make sure that we did not get so much that it would come over the top. We are also going to so the tiny bit that is left in your beaker, hopefully that is less than a 1/10 or 100th of a gram, that we would be able to measure with our electronic scale. We're going to let this filter, then we'll go from there. One of the things I would want to do is make sure that I've washed this a couple of times as well, just in case some of the potassium chloride that may be dissolved in the water is not staying in this liquid here. So we want to get this through, all right? So I'm going to wash this, and hopefully the material, the solid, isn't going to dissolve too much. But what I do want to notice, and want you to notice, is this. As this is occurring, look what is forming down here. Now, I don't think this is going to be very much mass, but what is happening to our filtrate is this. When we only waited 5 to 10 minutes based on our lab and the amount of time that we had to do this in the lab, when we poured this through, it was pretty warm. And so what we're seeing now is this material here is cooling off. So all of these tiny, tiny, tiny little bits of yellow, well, that's obviously some type of lead chloride. And so that was what got through the filter paper and yet is now solidifying at a cooler temperature. So those are some facts that you could probably put into some of your results in the Google Forms that you have to fill out to answer some of the questions. So we've rinsed this a couple of times. Okay, as that dissolves, or not dissolves, but finishes up and filters through, then we will take it out and we will put it into the oven overnight to let it dry out. Because at this point, we don't just have the solid, we have a lot of water in our paper. And so we've got to get rid of the water so we're not weighing that mass and adding it to our calculations. So we're going to take this out and we are going to put it in our oven. So we have transferred our filter paper. I've put the filter paper here on top of another filter paper and labeled it. And so overnight we will allow this to dry so that we will get rid of all of the water. So whenever we measure the mass of the filter paper plus the solid, we can then get that the total mass and then subtract the mass of the paper. So we've got this set just below 100 degrees Celsius, which is the boiling point of water. So whenever we open this up tomorrow morning, we should have some dry paper. We'll turn the fume hood on and make sure everything that gets hot gets sucked up through the ventilation and nothing catches on fire. So afterwards, we've got 3.44 grams after letting this sit overnight in the oven, making sure it is dry. So we've got a nice fine powder in there, and we will dispose of that properly. So this is the end of the KSP lab. So if you're looking at some information on the internet, if you've looked this stuff up on Wikipedia or some other chem tables, you'll find different KSPs for these lead chlorides and lead iodides. And when you do that, make sure you're looking at the temperatures because the KSP will change. And so our KSP, I did not give you the temperature at which this occurred on purpose because I didn't want you to be able to just look at it and engineer this backwards and figure out, hey, this is what it should be. So if you would, go with what's in the lab and do the math. If you have some trouble, go ahead and email me. But the KSPs, go backwards, find out what the KSP or the solubility was of the original amount of lead in the original 100 milliliters that we had that was a saturated solution. I sure wish you guys were here. There was a lot more on this lab we could have explained and went through a lot of math. So good luck, and we'll see you next time.